Okay, so we've worked out the terms quadratic in phi prime. We've worked out the terms that were linear in phi prime. Now we just want to look at the terms that are independent of phi prime. So that's that term over there. That's this term over here. And it is this term over here. So you can see that when we finish these last three terms, we've actually done everything. Okay, so let's say here, independent of phi prime. Okay. So what do we have? Well, we'll have an I integral d4x. And for this first term, I'm again gonna use my identity to swap the position of the derivative. So we'll have 1/2 phi naught d mu phi naught. So I've got an extra minus sign because I've swapped the derivative from the first phi naught to the second phi naught, and otherwise it's exactly the same. Then I've got minus 1/2 m squared phi naught squared. And then for the second term, we've got plus an integral d4x j of x phi naught of x. So that's all of the terms. Good. So let's just rewrite this slightly. I integral d4x will have minus 1/2 phi naught. And then we've got d mu plus m squared phi naught. Okay. And that's the first term on the previous line. And then we've got plus integral d4x, and we've got j of x phi naught of x. Good. Now, here again, we see our differential equation appearing, and this is minus ij. So let's see what we've got. We've got an I times a minus I. Well, that's a negative. So we've got minus integral d4x. We've got 1/2 phi naught and j. And then for the second term, we've got plus integral d4x j phi naught. Well, it's pretty easy to add these two terms together and just get 1/2 integral d4x j phi naught. Lovely. So now we've finished doing this rewriting. Let's just summarize it, okay? So let's summarize our answer. So what were we rewriting? We were rewriting this quantity over here. So is plus integral d4x j of x times by phi of x. And all that we did was we replaced phi by phi naught plus phi primed. Okay, that's all we did. And the result of doing this gives us, in fact, sorry, let me just rewrite this slightly just so there's no confusions. Let's just try to be as clear as we possibly can. So sitting over here, we've got the action evaluated on the field phi, and this becomes I times by the action evaluated on the field phi primed, and then plus 1/2 integral d4x j phi naught. So we're now ready to see what z of j evaluates to. So remember, z of j is equal to, it's an integral d phi e to the is plus integral d4x j of x phi of x. And now we do a change of variables in the path integral from phi to phi primed. And remember, it's the same change of variables. Phi is equal to phi naught plus phi prime. So that's what we're doing, okay? We'll have an integral. As we explained, the measure remains invariant. The domain of integration is invariant. Now we've got an e to the is phi primed plus, so I am just using this line above here, plus 1/2 integral d4x j phi naught. And what is this equal to? Well, the 1/2 d4x j phi naught is a constant, meaning independent of phi primed. Of course, it depends on x and t, but it's independent of phi primed. So I can take it out of the integral. So we've got a 1/2 integral d4x, j of x, phi naught of x. And then we've got an integral d phi primed e to the is of phi primed. And do you recognize this? This is just z with j equal to naught. So it's just z of naught. Okay, it doesn't matter if I call my integration variable phi or phi primed. So this is just z of naught. And what did we say that z of naught was? We said z of naught is related to the vacuum overlap on itself. So this is naught, naught, if you remember. And we said this is we're going to set equal to 1. So now, finally, we learn that z of j is equal to e to the 1/2 integral d4x j of x phi naught of x. That's z of j. And we have evaluated the part integral. So this is really very nice. And go back and study this computation. We absolutely recycled the logic of our one-dimensional integral. We've done nothing different. Now, this answer here is still not very explicit. And the reason for that is we still need to get hold of phi naught. And to get hold of phi naught, we have to solve this differential equation that phi naught obeys. We're going to do that in a lot of detail, and we're going to be able to write phi naught of x explicitly in terms of j of x. So that means we will nicely determine this final answer that we got for the partition function, for the path integral. We will be able to determine that completely in terms of j of x's. And once we've got this written as a function just of the j of x's, we'll be able to go back to the beginning. And what did we say? We said by taking derivatives of z of j with respect to the j's and setting j as equal to 0, we should reproduce this correlation function. And we claim that this correlation function is related to the time-ordered correlator of our quantum field phi of x as we calculated it in the operator picture. That's going to keep us busy for a little while, but we're actually going to evaluate this by working out what phi naught of x is. And in this way, we'll be able to prove very, very explicitly that we reproduce the answers that we got by working with operators in a Hilbert space. Okay, the only thing to discuss now is the exercises.